The speed of light, a journey through relativity and beyond. What would we witness if we approached the speed of light? Imagine boarding a spaceship, accelerating away from Earth, gaining speed at an unprecedented rate. What optical effects would emerge? What distortions would alter our perception of the universe? And if we attempted to surpass the speed of light by warping space-time, as often depicted in science fiction, what realities would unfold? These inquiries lead us to a captivating exploration of special and general relativity, unraveling the extraordinary phenomena that govern our cosmos. Acceleration and perception. At launch, our spacecraft is stationary, poised for departure. As propulsion ignites, we accelerate continuously, unhindered by the constraints of time. Though one might assume that excessive speed could become overwhelming, this is a misconception. Speed itself exerts no force on the human body, only acceleration does. Just as passengers in a train cannot perceive whether their train or another is in motion, within the spaceship, we remain oblivious to our velocity. We only feel the force pressing us into our seats as the thrusters propel us forward. As long as acceleration remains within a tolerable range, the journey remains physically manageable, even at velocities nearing the speed of light. However, high-speed travel presents an inherent danger: collisions. Even a minuscule particle striking the vessel at relativistic speeds would cause catastrophic damage. Fortunately, our spaceship is fortified with an advanced force field, deflecting hazardous debris and allowing us to traverse space unscathed. Optical aberrations and the warping of light. As our velocity increases, a striking optical phenomenon emerges. The stars before us appear to recede, as if converging toward a central point. The sky itself compresses. To visualize this, consider how rain appears when driving at high speed. Though raindrops fall vertically, forward motion alters their perceived trajectory, making them appear as if they are approaching from the front. Similarly, as our spacecraft accelerates, incoming starlight seems to shift forward, an effect known as the aberration of light. This aberration produces another striking consequence: the intensification of light at the front of our trajectory. The celestial bodies ahead grow brighter, while the sky behind us darkens dramatically. As we continue accelerating, another effect known as the Terrell-Penrose rotation alters our perception of objects we pass, causing them to appear skewed or rotated rather than simply contracted. Time dilation and Doppler effects. One of the most fascinating outcomes of relativistic motion is the Doppler effect. As we speed away from Earth, the light traveling from our home planet takes progressively longer to reach us. If we were to observe Earth through a telescope, time itself would appear to slow down. Human activity would be seen in slow motion, colors shifting towards red due to the stretching of light waves. Conversely, the stars ahead appear increasingly blue, their emitted light compressed as we move toward them. This relativistic Doppler effect provides a tangible glimpse into how motion influences time and perception. But beyond mere optical illusions, real physical effects take hold as we approach the speed of light. Time dilation, a fundamental principle of special relativity, dictates that for an observer aboard the spaceship, time flows differently compared to those remaining on Earth. If we were to return, we would have aged significantly less than those who remained on the planet. The discrepancy arises because our trajectory through space-time deviates from that of Earthbound observers. Length contraction and the illusion of distance. Another profound effect accompanying near-light-speed travel is length contraction. To an observer aboard the spaceship, the universe itself appears compressed in the direction of travel. Paradoxically, this means that interstellar journeys that should take thousands of years, according to stationary observers, would seem significantly shorter from our perspective. At sufficiently high speeds, the trip to distant galaxies could be perceived as nearly instantaneous. However, to those on Earth, millennia would pass in our absence. Visualizing length contraction is complex. If we were to approach a planet at extreme velocities, the planet's observed shape would appear distorted due to the delay in receiving light from its different regions. This distortion, rather than a simple shrinking, manifests as an apparent rotation, another manifestation of the Terrell-Penrose effect. Approaching the speed of light. As we accelerate further, our field of vision narrows, forming an increasingly concentrated focal point in front of us, while the space behind becomes enveloped in darkness. But can we ever reach the speed of light? The answer is unequivocally no. No matter how much we accelerate, light will always elude us, maintaining its constant velocity. From the perspective of an outside observer, we may appear to approach light speed asymptotically, but from within the spaceship, we remain in motion relative to everything else. Light perpetually outpaces us, remaining an unattainable frontier. Beyond the limits. Theoretical, faster-than-light travel. Despite the constraints imposed by special relativity, is there a way to surpass the speed of light? In theory, while no object can move faster than light within space, space-time itself is not bound by this limitation. General relativity reveals that space-time can stretch, bend, and even contract. This raises the tantalizing possibility of a warp drive, an advanced propulsion system that distorts space-time itself. Rather than propelling a spaceship through space, a warp drive would manipulate the very fabric of the universe, creating a bubble in which the ship remains stationary while space-time around it contracts and expands. This concept, inspired by science fiction, remains speculative, as it would require exotic forms of matter, negative mass, which has yet to be observed in nature. If such a mechanism were possible, an external observer would see the spaceship materialize from nowhere as light rays are bent around the curvature of space-time. Meanwhile, from within the warp bubble, the universe would appear severely distorted, with entire regions vanishing from view, lost beyond the reach of light. Conclusion. As we conclude this thought experiment, we are left with awe at the enigmatic nature of relativistic motion. While conventional space travel is constrained by the unyielding speed limit of light, the universe remains a vast frontier governed by laws that continue to challenge our understanding. Whether through technological breakthroughs or deeper insights into the fabric of spacetime, the pursuit of faster-than-light travel remains one of humanity's most captivating scientific quests. Until then, the wonders of special and general relativity will continue to inspire our imagination and push the boundaries of what we believe to be possible.